This is STA 381, Chapter 11, Section 8. Okay, so this is the last section of that we're going to cover in Chapter 11. So we're going to just kind of round out simple linear regression. You may have noticed if you were poking around, we didn't cover Section 6. There's parts of other sections that we haven't covered. So just keep in mind that we're really just restricting our attention to the sections that we've covered on these lectures. Okay, so one last thing to talk about it, which is correlation. So we're going to, first of all, if you look in the book, we're going to skip the discussion about the distribution of x and y being bivariate normal because we haven't talked about the idea of bivariate normality, which is discussed in Chapter 5. So don't worry about that part and just skip to the part that we're actually covering. The correlation coefficient, which was covered actually in an earlier section of the book, also in terms of regression measures the strength and direction of the linear relationship between x and y. And so here's one way to write R, which is given by this formula, and then you see a second way to write it. Notice that it does look rather computationally intensive to do by hand. So again, we won't be actually computing this by hand, but notice that we have x's and y's in both parts of it, so it is truly looking at that relationship, that linear relationship between the two. A couple things to note just in terms of formulas is that beta 1 hat, we can write beta 1 hat in terms of SST and SSX and R in correlation. They're very related to each other. And then we have R squared given right there in terms of beta 1 hat. So there's lots of different ways to write these formulas. And in fact, if you go Google this, you're going to see more. So keep in mind, if you happen to Google this looking for the formula and you see something different, don't freak out because it's not the one that you see in the book. There's lots of ways to manipulate these formulas and rewrite them in different ways. Okay, so correlation. And again, I see a actually notation issue here, so I'm going to fix it on the board. Correlation is the null hypothesis we can actually test, and we actually would use the Greek letter rho rather than R there for the population correlation. Okay, so actually we're looking at rho equals 0 versus rho not equal to 0. The appropriate test statistic is given by that t value that you see right there. So notice that we're still looking at the t distribution, and we're still going to be talking about n-2 degrees of freedom. So that's important, but notice that this note at the bottom says that the hypothesis test is the same as testing the slope equal to 0. So remember a couple of sections ago, we looked at the hypothesis of beta 1 equals 0 versus the alternative that beta 1 was not equal to 0. And so that's pretty important because what that means is you could go and do this one, and that's fine. Or you can grab the regression output out of R or whatever package you're using and use the hypothesis test for slope, because what it produces is the same t value and the same p value. So both of those are going to be the same. So I wanted to make sure that you knew that and you understood that. So we can use either one here. Okay, so we're going to go back to R and see where correlation comes into play there. That's the blood pressure example that we've been looking at in this chapter. Okay, so there's a couple different ways that you can get correlation out. First of all, the model, when you do a summary of the model, you'll say, wait a minute, I don't see an R there, a correlation anywhere. Well, R squared is really just correlation squared. So we've talked about R squared in terms of the percentage of the variability in Y due to the model. But if you take the square root of 0.6254, which is actually this value right here, the 0.7908, that is actually R. So there's a couple ways you can get it. Again, you could just get it out of the summary of the model. There's also a correlation function in R. So notice that I have correlation, core, noise, tilde, BP rise, Doesn't matter the order, by the way, for correlation. It matters for regression, but not correlation. And then my data set. And then we get this as our correlation value, 0.79. So let's talk a little bit more about what R means. It's actually different than what R squared means. Okay, so we're going to go back to the board. And we see some properties of R. First of all, R is between 0 and 1. Ooh, actually, that's wrong. That's another typo. This is typo day. R is between -1 and +1. So write that in your notes. R is between -1 and +1. R can be negative. R is unitless, just like R squared was, so changing the units will not change the computation of R. An R greater than 0 implies a positive association. So if you want to connect that to the scatter plot, this would be some sort of R greater than 0. An R less than 0 would be something like that. And that implies a negative association between the two variables. Finally, R measures the strength of the linear association between x and y. So what that means is that an R that is closer to either +1 or -1 means that there's a stronger linear association between the two variables. And what that means in terms of the scatter plot is that the points are hugging the line a lot closer as R approaches either +1 or R approaches the -1. And then an R that's close to 0 implies that there's no linear association between x and y. Now remember, we're talking about a linear association between x and y. I can put any old values into, as long as they're quantitative, into R Studio and pop out a correlation. But it may not mean anything if the relationship isn't linear. So you could get an R equals 0 if you truly have just scatter everywhere. I could also get an R equals 0 if I do something like that, where I have like a circular pattern going on. So that's one of the reasons why you plot your data. All right, so let's take a look. One more time, we're going to go over to the applet stat key this time and just fiddle around with a regression line. So I'm going to go over to stat key. There's two quantitative variables. I'm going to look at, let's take a look at, let's look at the hot dog data. This is the hot dog eating contest, number of hot dogs, you know, whoever won. So in 2006, somebody ate 54 hot dogs in a span of I don't know how many minutes. In 2013, somebody ate 69 hot dogs. Which seems incredible to me, and my guess is they probably threw up afterwards. I don't know. So, first of all, let's show the regression line. So there we have the regression line, and we look over here. We have standard deviations of x and y, sample size, there's our correlation, there's our R, there's our slope. Now pay attention to those values. So what I'm going to do to show you a couple things, first of all, that's a pretty decent correlation. The points are, you're probably wondering what's good. Good depends on context, really. This could be a good because I'd say there's a lot of variability in year to year. But in cases where you may be in the hard sciences or say in engineering, you might need an R that's actually a lot closer to 1. Social sciences, they're pretty happy with R's that are closer to 0.5 because there's so much variability in humans. I'm going to take, say, this point here in the middle, and actually I think I'm going to take the 2015 and I'm going to pull it down. Let's say that nobody ate hot dogs very well that year. And so what happens if I go down and let's say they have to eat a positive number of hot dogs. Let's say they only eat 6 hot dogs or something close to that. Notice what happened to both my correlation and my slope. They went from positive to negative. They went from a pretty good correlation to something that's pretty close to 0. So 1 point, 1 outlier can make all the difference in fitting a regression line and determining the correlation. So it's really important that you understand that when you plot your data, you need to check for outliers, because this guy is driving the entire regression line and the correlation coefficient. And if he was back up there where he was supposed to be, and I don't remember exactly where he was, but he was over at 2015, then we would have a value that made a lot more sense. Now, does that mean that you get to get rid of outliers simply because you don't like them? No, but you need to look at your data and explain, and try to explain, is it a typo? Was there something unusual that happened that year? And you need to go back and see what you can explain. And if you can't remove the outlier, you can remove it and look at the correlation and the slope and everything, and then put it back in and include both of those in your analysis. That would be a very fine way to be looking at your analysis. All right, so just to wrap up, what did we do today? We talked about the correlation coefficient and how you can test that, and how that test is equivalent to the hypothesis test for slope. We talked about what correlation means in terms of strength and direction of a linear relationship between x and y. We looked at where to find that in R, and then we looked at what happens when you play around with outliers and what happens to both the slope and the correlation. And this is the conclusion of this lecture.